Years back, when was it? 2000, 2001. 2000, 2001. I was invited to Shahid Behishti in Tehran, in Iran, to give a series of lectures. And, um, and at that time, they never heard of modular function spaces, okay? And I gave them this series of lecture on modular function spaces. Now the Iranian school on modular function spaces is by far one of the best in the world. Yeah. So why am I telling you this? Not because of modular function spaces. No, no, no. I went there in December. It was December to January during the break. And I don't know whether you know, Tehran is in the mountains. Okay? And the university is on the mountain. So you have to, either you are lucky and you drive to the department, otherwise you will have to walk. How come that we can walk if we have roads? Because it snows. So the last day, this is all to come to the last day. The last day, it was snowing. I mean, snowing the night before. I was staying in the hotel in the city, of course. So when I woke up in the morning and I looked through the window, I saw snow everywhere, a lot of snow. I said, Alhamdulillah, today I'm not going to give a lecture. And then the guy who invited me, a mathematician from there, Behzad Jafari, he came to the hotel to pick me up. So I told him, but it's snowing. He said, yeah, in Iran we don't, can be snowing, no snow, it makes no difference. I said, okay, in my mind, wallahi, in my mind I said, for sure I'm gonna go and nobody will be there because it's a lot of snow. In fact, that's why the car did not drive. We had to walk up the mountain. Wallahi, it's a true story. I will never forget this. The room was full. Everybody was there. Everybody was there. So you guys reminded me that moment. So I'm so proud of you. Did you get the paper I sent to Javid yesterday? Bayon's paper? So quickly, who asked me yesterday? Who? Somebody asked me. Yeah, so there you can see about asymptotic normal structure property. I will talk about that in the tutorial today. It's very important to see the connection. Is a very profound problem in fixed point theory, which is in order for us to investigate the fixed point property for non-expansive mappings, of course, we need to have more information on the minimal set. So the minimal set, knowing something about the minimal set helps us to investigate fixed point property. As of now, the last known result on that one is the famous Karlovich lemma or Karlovich-Goebel lemma, 1975. So we're talking about 50 years. Nothing was done. It's a very hard problem. It's a very, very, very hard problem. And of course, the Karlovich lemma is the one that led to the asymptotic normal structure property. So I will be talking about this during the tutorial, okay? But that's not what his name, Lim. Do you see Lim? Yeah, yeah. Yeah. So Lim was more interested into proving common fixed point of a commuting family. Anyway, so shall we move? So now, do you expect me to teach you modular vector spaces in 1 hour and a half, 2 hours, when it's a book? Do you think that I will be able to do that? Do you think? What do you think? I'm asking you. I'm honestly asking you. What do you think? Do you think I will be able to do that? Ah, she said yes. Oh, lie, she's good. I mean, when somebody tells you yes, it means he believes in you. Huh? He believes in you. It's hard. You are going to pay more for the picture.
Sure. But today is discount.
No, I will give you discount, but you're going to pay more.
Discount is cancelled.
Discount is canceled. so, so I put it for you just to give you a sense that two things. Number one, it's not possible for me in 1 hour and a half, 2 hours, to be able to describe what this object is. And as I told you earlier, at Shahid Beheshti, it took me like 5 days teaching them about this. And they published a PDF file. I believe you have a copy of it. And of course, that was the seed for the Iranian school on modular function spaces. It has a lot of stuff about, when I say modular function spaces, it has a lot about measure theory and so on and so forth. So this book was published recently, I think something like 15 or 19, I don't remember exactly. And I really want you not to ignore the concept of modular vector spaces. Now look at the difference. Modular function spaces, modular vector spaces, okay? So what did we do so far in this class? First, or in these courses, lectures, we started with metric spaces and how to look at abstract structures, okay? And then I moved to Banach spaces, and now we are moving into modular vector spaces. Modular vector spaces is not just generalization, because since the advent of the internet in '94 with Netscape 1.0, people, for a reason I don't want to talk about now, is started to come up with anything to gain citations and improve the metrics, okay? This is all due to this access to the data available digitally. But before 1994, especially in the 80s, late 80s, 80s, 70s, 60s, there was no digital data. So if you wanted to see something, you have to go and open a book, and there were some publications like Mathematical Reviews and Treblatt that we don't hear anymore. That's it, it's done. They killed them. So this time, the people were not motivated by improving H-index, citations, and so on and so forth. There was no such thing as iSci journal and so on and so forth, okay? So when modular vector spaces were done in the 50s by Nakano, it wasn't motivated by this kind of publicity or whatever. So I want you to grasp it. I really need you not to be blind on what's going on there, especially that it has major impact on PDEs, for example. My first colloquium talk, I'm so saddened that some of you did not attend, is about what's known as the energy, Dirichlet energy problem, which is connected to the P-Laplacian and modular function spaces, or what's known as variable exponent spaces. So what I will do today is an initiation. I will not teach you all the intricacies, okay? Yesterday I was very frustrated around midnight. I sent you the file around midnight. I was very frustrated because I couldn't put it small file. It was a long file. Okay, so shall we start? Yes? Okay. So remember, I'm going to give you the modular vector spaces, and modular function spaces are a special case of modular vector spaces. But modular function spaces were the origin of modular vector spaces. If you want to see the analogy, you have to go back to Banach spaces. Banach spaces were born with Banach in 1922, where he defined a vector with a norm. The concept of a norm is new, and as he did with metric spaces for the Banach contraction principle, he did it for vector spaces. He gave the norm properties of the norm, and then he said, he didn't call them Banach spaces, he called them class B, and he called them assuming that Cauchy sequences for the norm are convergent, which now we call completeness, okay? And so it was born in 1922, but we had all the classical, what they call classical Banach spaces, like L2 spaces and so on and so forth. They were known. It's not like weighted to, or C of k, which are the continuous functions on a compact set. So all this were known, okay? But they were not known as a norm, no. They were just known as vector spaces, function spaces, and with their classical. So here, so they are a generalization of what? Of normed vector spaces. So the module, and you will understand in a second why, the module is just something that generalizes norms. So you have norm is a module, and you have the concept of module, more general, okay? Of course, more general in what sense? In the sense that it corresponds to a structure that may help us understand some of the intricacies that the norm cannot, okay, that the norm cannot. So now, where did it start? This idea of module, where the seed, the original seed, it was in that famous paper by Orlich, 1931, okay? And what was the motivation of Orlich? Motivation of Orlich at that time was to come up with, construct Banach spaces that are not common, that are not classic. In fact, if you look at the books, the 2 volumes by Linzer Strauss and Safriri on functional analysis, okay, very famous 2 volumes. They were supposed to have 4, but they got into a disagreement, and they only wrote 2. And these 2 volumes, they are called classical Banach spaces. One is about sequential Banach spaces, and the other volume is about classical Banach spaces. So they were interested to find or build new Banach spaces. And why is that? Why do we want to build new Banach spaces? In general, they wanted to build these new Banach spaces to respond or to answer questions that they were putting where. Does anybody remember where these questions were asked? Yeah, I mean, you know the answer. Come on. Aha. I'm looking at your faces like, what? What is he asking? Anyone? You know the answer. Yalla. Okay, today is Friday. I'm going to be nice today. I'm not going to give you a hard time today. I'm not going to ask about the 2 words answer. So, anyway, it was in the famous Lvov school, Banach school. Remember? Huh? Remember the Scottish book? So some of the main beautiful results of functional analysis, like Anne Banach and so on and so forth. In fact, somebody who is maybe listening to us right now sent a question to Javid. His name is Mohammed Amin, by the way. And he asked a question about the Banach measure distance between Banach spaces, okay? And we were having an exchange with Javid yesterday, and it was confusing to me, the question, and they wanted it to be confirmed, and they asked my AI assistant, yes or no? and I send you the answer. Yes? So anyway, so the point is most of the foundation of functional analysis goes back to that group with some big names there. So Orlich wanted to come up with a new space. So first natural reaction was, what is LP? LP is when you take the integral of absolute value of f of x to the power p dx. Yes? So you have that p power, yeah, in the integral. Of course, the norm will be what? To the power 1 over p, fine. But what if I replace t to the power p, the power function, by another function with the same properties? Same properties. Look at my hand, okay? Increasing, convex, and so on and so forth. Equal to 0 at 0, and so on and so forth. So he came up with this idea, okay? So he said, now it's the integral of phi of absolute value of f of x dx. Yeah? So first. Now comes what? So this space is this one that you see right here, okay? And now comes what would be the norm, okay? Natural. You have a vector space. If you assume vector space, if you assume the condition that there is a constant lambda such that the integral of phi of absolute value of f of x over lambda, so you put lambda inside phi, then, or lambda time f, okay, for some lambda positive, this gives you a structure of vector space. Otherwise, it's not true, okay? The integral can be finite for f, can be finite for g, but when you put f plus g, it may be infinite. So to make it a vector space, you add that constant and it works, which you don't have in the case of p because alpha will come out with alpha to the power p, and then you have no problem, okay? So anyway, so here is the norm in the case of LP. And now when you go to phi, there is a problem. Right there. 1931. What's known as Orlich spaces, okay? We have a problem. What is the norm? So the norm in the case of LP is just the integral to the power 1 over p. But in the case of this one, you need little bit to work, little bit harder. It's more complicated and is not a direct norm like this one. 1931. Okay, 1931. Okay, so let's continue. So the connection between the integral and the norm, in the case of LP is easy. In the case here is complicated. I will give it to you, don't worry. Okay? But this point, that's what led Nakano to say, wait, there is more to the story. Not Orlich. So Orlich, he gave them a norm, and he showed them some nice properties of the norm, and that's it. But in the case of Nakano, he saw something more profound than the norm. Okay? More profound than the norm. So let's continue. So that's what I'm saying here by the work of Nakano, 1950. So we're talking about 31 to 1950, almost 19 years, 20 years before they saw, or somebody saw, that concept of module. Okay? The module was born with Nakano, not with the... Okay, so what is a module? So this was given to us by, what's his name? Nakano. Okay? So this is found with Nakano. So remember, all the work by the Polish school was more about functions. Now, what are the properties? And keep in mind, I forgot, keep in mind, just to help you, keep in mind that the definition that I'm going to show you, it follows this. This is, of course, for what? Modular function spaces. Modular function spaces, because the vectors are functions. I wanted to keep this in mind, okay? But to give you the properties. But we are no longer, it's like what Banach did with the norm, okay, from the classical examples before him. Now we are looking at what Nakano is going to do. Okay? Okay, so what are the properties? We have rho of x equal 0 if and only if x equals 0. Okay, you can, like we did for the norm, you have the semi-norm, semi-modular, and all this stuff. All this exists. I don't want to bother you with this. Okay? So let's move on. Next, you have this condition. Now problems start to become a little bit what? Complicated. Right there. So first, we don't have homogeneity of the norm. Right there. You have what? Rho of alpha x, which means that rho of x and rho of minus x are the same because of the famous absolute value that you have there. Do you understand? But you don't have anything because phi cannot allow a constant to come out. You don't know what kind of function you have. Third one is true in general, but most of my work is done when rho is convex. And therefore, the condition number 3 is replaced by this condition. Do you understand? I'm assuming that phi is convex, as I told you. By replacing t to the power p, I'm assuming that. But in general, if you want to go more abstract, you don't need to assume what? Convexity. But I only work with convexity. All my work from the fixed point theory point of view, of course, not the modular point of view. And also, as you can see, I want you to see something very interesting. Okay? Let's take y equals 0 for the sake of it. Let's take y equals 0. Then rho of alpha x will be less than what? Alpha rho of x, because rho of 0 is 0. And if you let alpha goes to 0, this one will go to 0. So we are looking at some kind of what? Of continuity of rho. And the one that is important, the one that is really important is this one, which is the left continuity at 1, okay? Okay, now what is the space? Remember what I told you. If you take f and g in the modular, in Orly spaces, rho of f is finite, rho of g is finite, rho of f plus g may not be finite, okay? So the space that we are working with is not the big space. So it's a space where we call it the modular vector space, which is the space where rho of alpha times x is finite for some alpha, You see it? So here, which is the same as this one, by the way. It's the same as this one. So we call it the modular vector space associated to rho. Okay? Associated to rho. Keep in mind, in the case of a norm, is the space, all of it, because norm of alpha x, alpha comes out. So, and also the norm is always finite. Module, no. Module can be infinite. If you wait a minute to go back, you see it? The module goes to 0 plus infinity included. So rho can be infinite. Now, there is one more property fundamental for modular vector spaces. I will mention it a little bit later, but let me say it right now, which is because of the lack of homogeneity, you have rho of x. Rho of x. What happened to rho of 2x? If you take rho of x over 2, just as an example, rho of x over 2 is less than rho of x. That's what you have there. I just showed you rho of alpha x less or equal than alpha rho of x. So rho of alpha x, alpha less than 1, is going to be bounded by rho of x. What happens if alpha is bigger than 1? Rho of 2x. It's the same, by the way, 2 or less. The problem is rho of x can be finite. Rho of 2x can be what? Infinite. And it can be what? Non-controlled. So to be controlled, rho of 2x, controlled by rho of x, I will show you in a second what it means. This is called, is central. for the people working in modular vector spaces or modular function spaces. Central. So this is known as the delta 2 condition. Now, you may ask me, delta 2, it can be any lambda, lambda bigger than 1. It's all the equivalent. Whether you have delta 2, delta 3, delta 4, but they all picked delta 2. All the people working in modular vector spaces or modular function spaces, they work with delta 2. But it's the same if you take any number bigger than 1. Any number bigger than 1. Anyway, of course, again, the beauty is to try to avoid delta 2. Because delta 2 makes working with modular vector spaces kind of easier. I didn't say piece of cake, no, but easier. Okay? So avoiding delta 2 will make a difference. There is a paper that a few mathematicians, I don't remember, I have it on my website, by the way, where they published a paper, and I had to what? Do a demonstration or proof that shows the same result without delta 2. And they called it the same title of their original paper, but I added without delta 2. Why I'm saying this? It shows you the importance for the people working in modular vector spaces or modular function spaces to try to work without delta 2. You will understand in a second why I'm saying all this. You will understand in a second. Okay, so what's the norm? The norm now. Okay, we need the norm. We have the vector space, what's known as modular vector space. Now we need a norm. Okay, so what is the norm? The norm is given to us by something called Minkowski functional. So it's a concept that existed before. Why am I saying this? Because of our friend Orlich. So when Orlich gave us Orlich function spaces or Orlich sequence spaces, vector spaces, he had a norm. He didn't wait for whom? For Nakano. Do you understand? And it was there where every time you have a special set, convex set that should be absorbent and so on and so forth, then you have a norm associated to the convex set where the convex set becomes the unit ball. So this is known. This is really something that was known before. And that's why here the properties of this set here, okay, which is convex because rho is convex, balanced because rho of minus x equal rho of x, and absorbance for any x you can find the lambda such that rho of lambda x is less than 1, etc., etc. Then you have this Minkowski functional, which is your norm but associated to CR. Now what happens if I replace R? In the case of norms, we have homogeneity, everything collapses. Do you understand? There is a relation between the ball centered at 0 with radius 1 and the ball centered at 0 with radius r. Do you understand? Because of homogeneity. But in the case of the module, we don't have homogeneity. So what happened to these norms? Okay, all of them. So they are all equivalent. And that's the relation you have right here. Okay? So these norms are equivalent. In this case, let us pick one of them because they are all equivalent. Let us pick one of them. And during the time of Orlich or even Nakano, they all took R equal 1. Okay? R equal 1. And they called it, they didn't call it Luxembourg norm. Okay? It wasn't called Luxembourg norm. Okay? It wasn't called Luxembourg norm. Luxembourg was a wonderful mathematician that when I arrived to California, Los Angeles, in 1987, I was visiting his regular seminar, and he's the one who found me the job in America. True story. I was just visiting America. I was planning to go back to France. And he's the one who pushed me to stay in America, and he found me the job in America. So why do we call it the Luxembourg norms? I know the guy, but why do we call it the Luxembourg norm? It's because he did with Zanin a very, you should find them. I think I have them as PDF, but I may not know. Beautiful 3 books, I mean, not books, 3 large publications on function spaces. and everything about function spaces. Okay? He set the tone, everything that you want to know about function spaces. So by respect to his work, they called that norm the Luxembourg norm. But it wasn't called Luxembourg norm early on. It was not. Okay? It should have been the Minkowski norm, but anyway. So, and you have these properties, the relationship between the norm and the module. The relationship between the norm and the module. Okay? So remember what I told you. This, what you see here, was known prior to Nakano. So it's very important to follow me here. Otherwise you get lost. I can lose you easy. You have to follow me. You're not going to find this written. What I'm telling you, I had to struggle to find it by myself. So you have to follow what I'm saying. This was known to our friend Orlich, okay, in the context of Orlich spaces, whether it's sequential or continuous with functions. Am I making myself clear? Including what? The norm, including the Luxembourg norm if you want. It was known. All this was known. The difference with Nakano, he put it in terms of modular vector space, in any vector space. That's what it is. Are you with me? Very important. Now, let's go to some examples. Okay? Some examples. So what are the examples? I'm going to go a little bit faster on this one. This is the Orlich function spaces, yes? And that I mentioned earlier. But now I set up what? The stage of what kind of function we want, etc., etc. Okay? So let's move on. So this is what? The Orlich function space. And as you can see, look at it. This is the Luxembourg norm. This is up, what's his name? This is up to our friend Orlich, not to Nakano. Huh? Okay? So this was known. All this was known. And if you take phi of t equal t to the power p, then you end up having the classical LP spaces. Okay? LP spaces. Ah, I forgot. After this was published, okay, this was published, Mushilak and Orlich, once Nakano did his work. So first, Orlich, nothing happened. People spent what? 19 years working on Orlich spaces. You have tons of publications on Orlich spaces. Okay? 1950, this famous work of Nakano on modular vector spaces. After that, Mushilak and Orlich, they came up with a beautiful example of not Orlich spaces, something else. I'll come back to this one. Very important. So let's continue. Yeah, so the next example I want to show you is the example of variable exponent spaces. Variable exponent spaces. A wonderful book. Up to few years before, I thought of it as the book. Now it's a piece of junk. Why? Because now I know what's going on. Once you know, at the beginning you are impressed by a book, and once you start to know the things, you say, wait a minute, this is not a good book. Very important, okay? So this book, I really considered it as the Bible for understanding variable exponent spaces. But now, knowing what I know, especially with our friend Osvaldo, this book is extremely bad. But for somebody who doesn't know, it's okay. I mean, you should have it, okay? It's available, huh? It's a PDF. And look at the title, Lebesgue and Sobolev spaces with variable exponents, okay? So let's continue. I have this book, by the way, if somebody's interested. Okay, so now what happened? You go back to 1931, okay? To that famous paper by Orlich. And there, I was telling the people during my colloquium talk, I had a visitor from Turkey, Nesreen, and she wanted to work with me for a year. She was doing her PhD in Turkey, and she wanted to work with me. So I was looking for a nice problem for her to go back fast on this story, and I saw something very interesting from this paper, okay? And what's interesting is that he took here, he took this example without this one, okay, 1 over Pn, okay? And he took it with the power n. So instead of to the power p, that was the classical little lp, now he made p variable. He put it equal n. Huh? So it's not an Orlish space. The problem is, I'm puzzled till today, he didn't do anything. He just gave it as an example. In the same paper in 1931, he gave it as an example, and then he moved on. He didn't even touch it. Okay. So why do we call it variable exponent spaces? Because the exponent is variable. If Pn is bigger than 1, of course we don't want Pn to be equal to infinity, yeah? But if Pn is bigger than 1, this module is convex. And it's really a module. It's very easy to see that you satisfy all the properties of a module, okay? Moreover, what? What do I want to say? Yeah, moreover, there are publications where you don't have 1 over Pn. Some, they have 1 over P of n, some do not. I'll explain. I don't think I'm going to explain here, because this has to do with PDEs and the Laplacian. So there is a reason, anyway. So you see, now, you see the rho star? In the rho star, there is no 1 over P. Okay? What's interesting, and this is not clear, what's interesting is that if you take, this is another module, if you take this module and the previous one, they give you the same space. The vector space is the same. Not the same constant that you are going to have for which rho of alpha x is finite. No. It's not the same constant, but still you are in the same. The vectors here and the vectors here are the same. And the Luxembourg norm for this one and for the other one are equivalent. Okay?
Hello.
So this one, this space, now we can look at as functions. What happens if I take the continuous variation of little lp, same as little lp and capital Lp? Do we have one? Yes. Here it is. So you have it also in this case, where you have functions now measurable, blah, 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 all of it. And again, as I said, you have the same problem whether you have 1 over P of x or you don't have 1 over P of x, okay? And you have now the capital LP of omega, okay? And the book I showed you, they work with this, not with little lp, okay? The whole book is about PDEs and so on and so forth, therefore functions, and therefore they're working with what? Capital LPs. And as you saw, it has something to do with Sobolev spaces. So there is a definition to consider for the Sobolev what? Case. I don't think I put it, but we'll see. So as I said again, you have the rho star without the 1 over P, and then you have the same space, exactly the same as the other one, both, the same vector space, okay? And the norms are equivalent, the Luxembourg norms. But these two are different in some sense, Now, we're going to get into something very interesting, which is, look what I'm writing now. Rho P of this UN or UK goes to 0, but rho star P of UK does not go to 0. And here is the example. Okay, very simple example. It's going to get a little bit tricky now. We are talking about convergence in the sense of rho. Remember, rho is not what? You don't have homogeneity, and you don't have the triangle inequality. And if you remember at the beginning, I told you what happened if you don't have the triangle inequality. Things get completely what? Messy. And if you are not careful, you are thinking in terms of what? I did tell you all this at the beginning. You are still thinking in terms of what? Distance. If you think in terms of distance, you are off. And it happened to people who published papers. And by the way, why they publish these papers? Because the reviewer is not good in modular function spaces or modular vector spaces. So here is an example of what is the Sobolev space I was referring to. So what you do, you have the derivative of the function, yeah? So think of it as one variable. Forget about several variables Rn, just on R, functions on R, you have the derivative, and the derivative also belongs to the LP space. So the function belongs to LP, and the derivative belongs to LP. You have the Sobolev space W1, okay? And what you do, you define the module. Which module? This one, which is rho of u plus rho of the derivative, okay? If you have now more than one variable, so you have the gradient, and in order to define it, you have to take what? The module of the gradient, and the one that traditionally we take is the, or they take, not me, they take is the Euclidean norm of the gradient, okay? So just if you take the Euclidean norm, you end up having what? A function, real, and then you take the rho of that gradient. That's what they are doing, okay? And for a reason. It's not like they are doing it just for the sake of. Okay, so same. If you ignore the 1 over p, then you have another module, and the two modules are kind of equivalent in some sense. Luxembourg norms are equivalent. They define the same topology, and they define the same vector space. Okay, so it gets complicated in the sense that they become natural for defining what's known as the Dirichlet energy integral. The Dirichlet energy integral is this one. So the Dirichlet energy integral is this piece. And the problem is to find what? The infimum or the minimum of this integral for u belonging to a certain set. Okay? That's what I was talking about in the colloquium. Huh? So it's natural, that's what I want to say. Huh? And the 1 over p is important. If you don't put it, you get a different Laplacian. The regular Laplacian is when p of x is equal to 2. Okay, you get the Laplacian. But if p of x is not equal to 2, you get what's known as the p Laplacian. Huh? P Laplacian. Okay. So we have some examples. Uh-oh, what's going on? Oh. Now, we want to have some kind of convergence. Yes? So I already gave you a hint. Rho, if you remember, rho of uk goes to what? To 0. So from the beginning, when I got to know this with Kozlovsky, I was visiting California when I just arrived. Kozlovsky was, in fact, visiting under Fulbright scholarship. He was visiting Luxembourg. And the reason is because his work is a PhD, or what they call in Poland, the habilitation. It was on modular function spaces, okay? Modular function spaces with Mushilak, in fact. With Mushilak. So when he arrived to Caltech to visit Luxembourg, he started working. Caltech and USC, University of Southern California, are very close. One in Pasadena, the other one in Los Angeles, but very close. It's about 1 hour between the two. And he was working with Shimon, okay? Shimon Rake. And what they wanted to do is to start fixed point theory in modular function spaces. Start. So if you want to start fixed point theory in modular function spaces, the first theorem that you want to think of is Banach contraction principle. Okay? So to show you the divine intervention from heaven, Amin just arrived at that time to Los Angeles. Same time. They were working already. But when I arrived there, Shimon asked me, said, Amin, we are struggling, me and Wojtek, on this problem. Can you please help us out? And that's how I got initiated to modular function spaces. I told them I have no idea what is this. You explain to me, and I'll see what I can do. It's heavily dependent on measure theory. You can see the paper, the original paper. And as Izhar reminded me a few days ago about the Fatou lemma, and the understanding of Fatou lemma for a student who is taking measure theory, and then the video I made online for it is it gives you a sense of sometimes not understanding measure theory the way it should be. Okay, we teach it, but we don't go beyond the surface, unfortunately. So anyway, so I got involved. Okay, I got involved with them. And what are the ingredients that you need for Banach contraction principle? You have the iterates, and you want to show that the iterate what is Cauchy. Yes? But wait a minute. Why do you need iterate Cauchy? You need to have it Cauchy so you can say through completeness that it does what? Converge. Okay. And then you want to show that the limit is what? A fixed point, and then show that you have only what? One fixed point. These are the ingredients, okay? So it is central to have what? Cauchy behavior with convergence. 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 You need to have that. So we need to define that. Wait a minute. Are we going to do it with respect to the norm? No. Why? Because it's done with the norm. It's done. Everything is done. So we are not working with what? With the norm. We want to work with the module. You see? So that's why from the beginning we needed to work with this. Now, was it us doing it? No. There is a famous book by Mushilak and is it Mushilak and Orlish or just Mushilak? I think it's only Mushilak. Lecture notes, old one, where he talks about this, and he inspires himself from the book or the notes by Nakano. Okay, so this was known. It's not like we came up with something new. So what is this modular convergence? Modular convergence. So we're motivated by all this, but we used what was known. Okay, so here it is. Okay, so you have the modular convergence, and you have the norm convergence. Do you see it? So we have the modular convergence, and we have the norm convergence. This was known. In other words, we just used what was out there. What's interesting, no. What is interesting is that if you converge in norm, you converge in the module. But you don't have this implies this, except if you have delta 2. Except if you have delta 2. If you have delta 2, the two convergences, they coincide. Oh, that's what I wrote right here. Okay? So if you have delta 2, the two convergences coincide. Otherwise, they are different. So keep in mind, if you have this one, you have this one. But if you have this one, you may not have this one. Okay. So now I'm talking about what? Delta 2. What are the properties of delta 2? There are many variants of delta 2. The one that is very common, that I like very much, is this one. Okay? Sometimes it is satisfied, sometimes it is not satisfied. Okay? So there are variants of delta 2. So this gives you a control of rho of 2x compared to rho of x. That's what it means. Rho of 2x over rho of x is bounded, okay, above. Now, if you go back to the case of variable exponent spaces, this is true in any vector, modular vector space, okay? But in the case of modular exponent spaces, variable exponent spaces, this is equivalent to the one I told you before. This one. This one. This is if and only if this. But not in any modular vector space. That's not true. Okay? That's not true. Anyway, and one more thing, there are two numbers in any paper written on variable exponent spaces. You are going to see two numbers, whether it's sequential or continuous. You are going to see these two numbers, p minus p plus. Okay? P minus p plus. So p plus If it's finite, you have delta 2. Why is that? Because what is rho? Rho is going to be the integral over 1 p of x, absolute value u of x to the power p of x. But if p of x is bounded, and if I put a 2 inside, the 2 comes out with the plus. And the k you generated using what? The p plus. Are you with me now? You see it? So remember, our p of x are all between 1 and infinity. Yeah? That's why. Okay? So it holds if and only if. Huh? Okay. A little bit more about topology. Huh? So now we have convergence. Yes? So when I was doing this paper with Shimon and Kozlovsky, that's what we did. We just did what? The convergence. Okay? Now, to take them, that was Banach contraction principle, and you will see it. But to take them to what? The next level. They are now listening. They are only helping me with the modular function spaces. To take them to the next level. What is next level? From Banach contraction principle. What is the next level? Huh? Wallah, I didn't hear you. Excuse me. No. No. Huh? Who is talking? Yes. What's that? No. You know the answer. What happened? We have Banach contraction principle. What is the next big thing? No. No. I mean, I love you guys. Wallahi, I love you. My students, when I ask them this kind of questions, they start telling me all the answers. I tell them, okay, let's open the book and start saying all the words. You know what? We'll hate it. Sooner or later, we'll hate it. It's 1965. Come on. So it's to go from contraction to what? Thank you. So if you go to non-expansive, or Kirk fixed point theorem, you need normal structure property. And normal structure property, the convex can behave very badly. And I know how to avoid that, not to work with the convex sets. Using what? Convexity structures. People did not know this. They never heard of this. So my point is, I will mention it at the end. I called it the compactness in the sense of balls, but this is the reason why. I mean, without putting it, because I couldn't put it. But anyway, so these balls, I needed them for that reason. Only for that reason, for non-expansive mapping, I needed the balls. And specifically, the closed ball. They are not closed, nor that they are open. But we preserved the same wording definition as the metric case. Yes? Are you with me? Now, this was done in 1988. A year ago, I started working. We went back to this that you see there, and myself, Osvaldo, and two Czech. One of them is in the US, in Ohio. His name is Jan. And the other one is Alex in Czech Republic. And we finished the paper. But what happened is the first time it happened to me in my career that one of the authors died. So we were like this. What to do now? Okay, it was Alex in the Czech Republic. He passed away. And the paper, we're going to submit it now. I mean, now. But it's a paper, I had to make a stop because we arrived to 40 pages. And they said we have to cut because it's too big. But it's mostly about what? Topology of modular vector spaces. You see? Topology of vector space. So it wasn't done before. And there is a motivation why, a reason why. Oh, let's continue. So it's not known. That's why I want to say the word is topology, but don't pay attention too much to the word. It's just seeds. We are not there yet. Okay? So anyway, all this is coming from this paper, by the way. And also before, what we did is set is rho closed, because I needed that for the Banach contraction principle. Rho closed if and only if rho convergent, the limit belongs what? to the set. Okay? We needed that. We did not see it from what? Topology point of view, but we put it as a definition. Yeah? So for example, the balls are row closed if and only if rho satisfies the Fatou lemma. So the Fatou lemma, if and only if, you have the Fatou property if and only if the row balls are closed. I'll give it to you, don't worry about it. So anyway, so this is just the beginning. As you can see, property I, we used it in 1988. But we did not know that it was a topology. We just used it, okay? Okay, so the Fatou property. If xn converges to x in the row sense, then you have rho of x minus y less or equal than the limit. This property is known in modular function space. It was known prior to Nakano. It was known. And to help you out, if you have the case of Orlich continuous functions, capital L phi, then what you have there, instead of row convergence, because there is a subsequence such that converges in measure, then you have the classical Fatou lemma with the measure. Do you understand what I'm trying to say? So there is a connection from the work of Orlich. But they kept it what? In modular vector spaces. They kept it in modular vector spaces. Okay? And this property holds if and only if the balls are row closed. The balls are row closed, meaning that if xn converges to x in the sense of row, x belongs to the ball as well. The xn's are coming from the ball. Now, as we did, when I wanted to go from Banach contraction principle to Kirch's fixed point theorem, 1988, I needed what? But I needed the geometry, because the Kirch's fixed point theorem says what? That you need normal structure property, which is a geometric property. And in fact, we don't know that property very well. What we know is that if you are uniformly convex, or uniformly convex in every direction, then you have the normal structure property. People focused on the geometry part, it implies the normal structure property. But it's not easy to work with the normal structure property. It's a very complicated property, extremely complicated. In fact, that's why James' example, the renorming of Littler 2, was wow, okay, for them. Okay, so now, what is strict convexity for rho? What you see there is similar to the norm. If you replace rho by the norm, you get same definition, exactly the same definition. Okay? So what comes next? Uniformly convex in every direction. So you have the definition similar to what I gave you yesterday. And if you remember carefully, because I was thinking about today, is that I gave you a definition that is not classical of UC. Is equivalent but not classical. And the reason why, because this definition can be adapted in metric or non-linear. Okay? So now what is the classical one? But to understand the classical one, the direction in this case is going to be z1 minus z2. You have 2 points, and the direction is this one. Do you understand? When we say uniform convexity in every direction, what is the direction? It's z1 minus z2. It's this one here. You have the vector z1 and z2, and this is the direction, okay? So if z1 is different from z2, this vector is not equal to 0. Yes? Okay? So if you put h equals z1 minus z2, it becomes what? Y is x minus z1, and x minus z2 is y plus h. So this, the norm of this one will be less than r, the norm of this one will be less than r, and the norm of this one will be less than 1 minus delta times r. Okay? So this, you see this with this and this is the classical what? You see. The classical definition of uniformly convex in every direction that I started with in 1983 in Zisler's paper, okay? The first paper I read in my career, That is the definition. That is exactly the definition. But this definition is not adapted to matrix spaces. Why? Because what does it mean, y plus h, if you are in cut zero spaces? I have the middle point, but what is the sum of 2 points? Yes? Do you see the problem? And the same goes here. What is y plus h over 2? So this is not adapted definition to nonlinear what? Cases. Okay. So now you have this definition, the classical one. And what I just told you is exactly what you read here, including what? Cut zero spaces, which is a wonderful example where we can talk about UCID, but using the other definition, not the one, the traditional one, the classical, which are equivalent in the case of linear stuff. So now, what's the relationship between UCID and SC? If you are UCID, you are SC. Okay? You are. But of course, if you are SC, you are not UCID. That's the case of linear, because rho can be a norm. The modular can be a norm. So no, there is no hope that they will be equivalent. They will be equivalent. In general. So if you have UCID, then obviously the Chebyshev center that we have to define will have at most what? 1 point. Remember I explained this to you. So that's how we get what? The normal structure property. We may need some compactness. Why? Because we need the Chebyshev center not to be what? Empty. Because why? The minimal set. So I need tools to prove the existence of a minimal set. Therefore, I need some kind of compactness. Once I have the minimal set, I need to show that the minimal set is what? Diametral. Like what's happened with Kirk. So we had to establish A and B. Do you remember A and B for the minimal set? Anyway, so A and B, we have to establish it. Once we have it, the B tells me what? Because he needs A. The B tells me what? It tells me that set is diametral. And if the set is diametral, normal structure property forces the set to be reduced to 1 point. Once it's reduced to 1 point, it is a fixed point. You see how it fits? And the same goes for the third property, which is Karlovich lemma. What Bayon did, he just said, I want it to fail Karlovich lemma, and therefore he came up with the concept of what? Of asymptotic normal structure property. So if we know more about the minimal, I assure you will become star in the community of fixed point theory. You will become star if you can find anything new about the minimal set. Don't waste your time on this. It's too complicated. But in case you are coming up with anything to help us understand more the minimal sets, then wow. So anyway, so this is a paper where what I did, there are 2 papers. They came at the same time, okay? First one, working with Shimon and Kozlowski, or Wojtek, about establishing Banach contraction principle at the beginning of fixed point theory for non-expansive mapping. That was the first one. Second one, I said, okay, fine. I mean, this is just putting the assumptions, the hypothesis to make it work. I need concrete examples. Again, the divine intervention. At the same time, this Chinese mathematician was visiting Norway. So you have Chen Shutao, Amin, Shimon, Kozlowski, all at the same time. At the same time, if I delayed my PhD just 6 months, I wouldn't have met these people. And by the way, even my trip to California was done because the chairman is a big name in fixed point theory, close friend to Bayon, Ronald Bruck. He came to Paris, and he was asked by Bayon to be in the committee of my PhD. And when I finished, he said, do you want to visit us for a year? That's how it happened. Why am I telling you all this? Sometimes, and that was my colloquium, which is the accident in life, okay? My first encounter, second encounter, third encounter, and fourth one, is that in your life, you meet some people that will take you into a different route that can be very rich if you accept to communicate and listen. So now, let's go back to Chen. I put Chen Shutao, I put Aimé Kamsi, I put W. Kozlowski, and I put Chen Shutao. And the reason why I put Chen Shutao, because I found out later on that in some of his papers it's S. Chen, and in some of his papers C. Chen Chutao. I mean Chutao, sorry, C. Chutao. So I am completely lost to whether he's Chen first name or Chutao first name. And he's in Harbin University. He has an amazing story. I will not tell you about it now, why he got interested in this. But what's interesting, he was an expert. I mean, Polish people, they love the guy, okay? There is a story, a beautiful story, but let's move on. And he is good. He's very good at Orlish spaces. Ask him. So he said, okay, me and Kozlovsky, we went to see him in Northridge, and we say, Chen, we have this problem. We have this property, okay? And we want to see if you can come up with some characterization in Orlish spaces, okay? But we don't want delta 2. That was the condition. Can you help us? Why? Because Kaminska showed that if you have delta 2, the norm satisfies the same properties. It's really back to the norm. We don't want that. We want to show the people that the norm is bad and the module is rich in the case of delta 2. We have some kind of originality, okay? And he said, okay, fine. So first example he did 2 examples. First one is when phi, the function that gives you the Orlish modular, okay, the function phi, if it's strictly convex, so they have this concept. This is well known. So in the classical theory, if phi is strictly convex and delta 2, phi satisfies delta 2, then you have the norm, which is strictly convex, and you see they are equivalent. Now we told him we don't want delta 2. He said, okay, if you don't have delta 2, and we don't want it for the norm, which is very complicated, we want it for the module, because we are working with the module, he gave us this theorem, beautiful, okay, which is this one that you see here. And what's amazing is that UC and SC, I mean UC, just UC, don't worry about it, and SC are equivalent, which is not the case for norm in vector spaces, in the classical norm, in just normal norm, okay? The proof is very technical, very technical. Okay, so this is Kaminska's result with delta 2. See it? If it's strictly convex and satisfies delta 2, then the 3 also for the norm, okay? Now, this, I wanted to show it to you to explain what's happening now with uniform convexity. I showed it to the people. So this goes to Clarkson, okay? 1936. So Clarkson used this inequality to show that capital LP is uniformly convex. I talked about it, okay? And in the case of capital LP, there is no need to worry about modular because the module is exactly the norm up to a certain power 1 over p, okay? They are the same. So where did he get this inequality? From the, I told you about it, from the parallelogram identity. And how do we see now the proof, as I did for Hilbert? You get it from this term. If this is bigger than epsilon, okay, this one, then you're going to have this one less than 1, 1, half 1 plus 1, 1 minus this one. This one is what it gives you the delta of epsilon. You understand? This term, this one, fundamental. Now what happened for variable exponent spaces? I wanted to pay attention to this. What happened when p goes to infinity? Then the 2 comes out. It becomes what? 2 to the power what? P. And if p goes to infinity, in the case of variable exponent spaces, this is exactly to avoid to have or not to have delta 2. If I don't want delta 2, I know p will go to what? To infinity. And if p goes to infinity, what happened to this term? What happened to this term? Once I take the 2 out, what happened? It goes to where? And if it goes to 0, I lose what? The uniform convexity. Early on, 1988, I said, wait. Why are we taking 2 out? So I suggested, at that time, no. Let us keep the 2 inside. Don't take it out. But in this case, instead of having the norm of x minus y in the definition of uniform convexity, it becomes what? The norm of x minus y over 2. Inside. Norm is homogeneous, makes no difference. But for the rho, it makes a difference. Early on, I asked this. 1 with the 2 inside, 1 without the 2 inside. I call this one UC1, and they call this one UC2. So it's a new uniform convexity. What did I ask our friend Chen? I asked him with the UC2. Can you give me an example with UC2? That was not known before. It was not known. And of course, on the top of that, I don't want delta 2. So anyway, this is when p is between 1 and 2. This is the inequality. It was discovered later on, okay? Our friend, what's his name, Clarkson, to prove LP with p between 1 and 2 is the uniformly convex. He used some heavy tools. But this is very important for the people working in, look at this one. This is the famous what? Variable exponent sequence space. Okay? So it was done by Sandy Rasan. This is beautiful inequality that I worked a lot on. So here we have this result, okay, for little LP. Okay, let's move on. Now, of course, sorry, I forgot. This is not Orlich. Now we're talking about variable exponent spaces, okay? Variable exponent spaces. You have something for the capital LP, same, strictly convex and so on and so on. Same example, okay? And I want to show you this. This is a technical lemma where rho of u is less than r, rho of u is less than r, rho of u minus v over what? 2 inside, bigger than epsilon r, yes? Huh? You have this. So it's like 1 minus delta times r. But what I put in red is to show you that the delta does not depend on r. In the general definition, there is an r in the delta. But when we do calculations for variable exponent spaces, we did not find r. It's very important for the proofs, the technical proofs that we are looking for. I mean, we can work with r or without r. So that's why I said you have this and this, but in fact, this one implies this one, but they are the same now because the delta does not depend on r. Let's move on. Here we have what? Modular uniform convexity. I'm done with strict convexity. I'm done with what? With UC, and now I'm going to uniform convexity. Remember all this, I'm keeping an eye on 1965. Yes? All this, okay? So here we have what? The definition. As you can see, rho of x minus y. Rho of x minus y, it means I'm dealing with UC1 or UC2? Which one? UC1. So that's why I called it here UC1. Are you with me? So if I go to the next one, oh, and we have this property. I saw it in that famous book I told you about. Similar, but it's different, slightly different. So I called it UC1 star. Okay, so look at this one now. Look what happened here. So we have the 2 inside. This was not known. If you look at the books on modular geometry, you don't see this one, you see UC1. So of course, if you have delta 2, the 2 are the same. If you have delta 2, if you don't have delta 2, they are different. Why? UC1 comes from usually bounded P, and this one can be for unbounded P. okay? Which allowed us to solve a problem that was 50 years old recently. So it's a really beautiful property on this with the two inside. And we have the UC2 star, the same, by putting, instead of having rho of u minus v, we have now rho of u minus v over 2, okay? Okay. So this connects, for example, Orlich. So same examples. We have Orlich, variable exponent spaces. Orlich, we have this definition of very convex. I had no idea this definition existed. It was Chen who did it. Chen said, this is the definition of very convex function, and from there we proved something. So now, do we have an example? Always. Do we have an example of a very convex function and which does not satisfy delta 2? For Orlich, I'm talking about. And they give us these two examples. Okay? They are very convex, but they fail delta 2. So now what do we have? Very convex is equivalent to UC2 for the rho, of course. What if I throw in delta 2 here? Then it becomes the norm. You understand? Is uniformly convex. And this is the, again, same paper where this is done without delta 2. Okay. Now, let's go to the variable exponent spaces. What's going on? Variable exponent spaces. We want p minus to be bigger than 1. Why? Because if p minus is equal to 1 on a set of measure non-zero, take functions where the support is only on that set. So I have the variable exponent space. And take a set of measure non-zero where the function is equal to 1. Okay? Then on that set, and I take functions only with support in that set, 0 everywhere, but only on that set. You will find a copy of L1 inside your space. A copy of L1 inside your space. And a copy of L1, it fails all the geometric properties. So all the geometric properties are bad. No strict convexity, no nothing. Okay? And the same goes for L infinity. Okay? So we don't want this to happen. That's why we have that assumption that the essential env is bigger than 1. We want to avoid not to be equal to 1. And we have now the module with 1 over p of x. So we have UC2 star, which implies UC2. Now we go to fixed point now. Now I just gave you, I missed a lot because I couldn't, okay? So now let's go to fixed point now. Now let's start looking at fixed point in modular sense. So first of all, we're looking at functions which are Lipschitzian in the sense of the module, not in the sense of the norm, because what's the point? In the sense of the norm. So we have what's known as a modular contraction. Okay? You will find papers out there where they put a lambda here. Okay? There are some authors. They do that. Wrongly, of course. But especially the guy who did modular metric spaces, he put a lambda and he wanted to agree with me. I mean, not agree, disagree with me, and I gave him a hard time. Now, okay, we have a problem, as I showed you, kill it by taking boundedness, and you're okay. What about Caristi? Caristi, you cannot avoid it. After what I did, you start to see the inside working. Why? Because you need a triangle inequality. How are you going to have a partial order? So in the proof, remember the Kirk's problem. Without the additivity or the triangle inequality, of rho, you get stuck, really stuck. And in fact, it fails. Because I told you about the square. Yes, the original problem of Kirk is false. And rho can be a square. Yeah, can be. In other words, d squared is a module, the norm squared. Norm squared is a module. So now we go to what? After we are done with contractions, we go to non-expansive. But as you can imagine, we did not do just this. We did a lot of things. Like what? Like asymptotic non-expansive mappings, semi-groups, and so on and so on. We did a lot. That's why you have the book. It's not just this. But I want to give you a feeling of how it started. Really a feeling. Putting what? An analogy between what we did between Banach contraction principle, Karisti fixed point theorem, and 1965, and modular vector space. I wanted to show you the parallel between the two. And if you don't pay attention to 1965, your research will stop with the theorem I just showed you. You will stop there. But because you know 1965 and beyond, now you can continue the research. Do you understand? Okay, so here is now a rho non-expansive. But for rho non-expansive, you cannot escape it, because a norm is a module. You have to go back to the theorem of Kirk and see all the ingredients that you need. But the ingredients are normal structural property and some kind of compactness. Convexity, I have it. Rho is convex and domain is convex. Okay? The other one, no. The other one, I didn't. You see it? C is not convex. It's very, very close to what's going on in what? In the case of classical fixed point theorems. But in the next case, we are going to assume that C is what? Convex. Subtleties that you have to pay attention to. Question. Non-expansive for the module. What about non-expansive for the norm? Is there a relation? Luxembourg norm. Is there a relation between this and this? Lipschitzian with respect to the module, Lipschitzian with respect to the norm. Okay? All this, we started right there to ask these questions to understand what's going on. We don't want to build something that is obvious. That is the first result. Now, if you have rho of lambda less or equal than rho of lambda, then it is non-expansive for the norm. Now, this answers the crazy guy who gave me a hard time. He wants to put the lambda, his name is Chishakov, and he came up with the concept of modular metric spaces, and he put the lambda. Once you put the lambda there, then there is no sense of talking about non-expansive for the module. In fact, it is non-expansive for the norm, in his case for the distance, okay, and the Luxembourg distance. So I told him, you should not. You should only do it for lambda equal what? 1. Don't do it for any lambda, okay? Some people fell for that. Not only him, some people fell for that. They put for every lambda, and in fact, why? Because they wanted to be what? Non-expansive for the Luxembourg norm. But once you are for the Luxembourg norm, use what? Classical theory, and you are dead. Right there. It's not interesting. So the question is, do we have an example where it is non-expansive for lambda equal 1, but not for any lambda? Meaning what? It is non-expansive for lambda equal 1, but not for the norm, yes? So this way, the two classes are different. Okay. Here is the example. Okay. This was done 1988 in that famous paper with Shimon and Wojtek. What's interesting, I did not know this because I was new. I was just initiated to modular function spaces. In fact, in that example, which was published in 1989, in that paper, what we use is, we called it Mushilak-Orlich space, but in fact, is a variable exponent space. Do you see it? It's a variable exponent space. So look at it. You see? This is your P of x. We did not know. I did not know. And nor that what his name, Shimon. And of course, Shimon did not know anything about this. But also Wojtek, who is coming from Poland. Okay? So here is the example. And what you see here is that the norm, it's linear. T is linear. So T of 0 is 0. But the norm of T of f is strictly bigger than norm of f for this f, the indicator function of 0, 1. Anyway, but let's move on. So the two classes, we're very happy. Why? Because the two classes are different. So it's meaningful to investigate non-expensive mapping for the modular. It was meaningful. Oh, by the way, let's go back. Sorry. Pay attention. What is the supremum of P of x? I did not know this at that time. Now I know. What is the supremum? What is x? What's the omega? Omega is what? 0 what? Plus infinity. Therefore, what is the, and P of x is equal to what? X plus 1. Therefore, what is P plus? The supremum of P of x. What is it? Obviously, what is it? Yeah, it's infinity. So, for sure, 100%, we fail what? Delta 2. So here, for this module, we don't have delta 2. Okay, let's continue. Now, here is the theorem. So we start now. First, uniform convexity. If we have uniform convexity, we have fixed point. That is Browder and Goeth. Yes? So we have it. This goes back to 1988 paper, the original one. Okay? So you need UC1 and you are okay. You have everything nice. And we use almost the same ingredient as Goeth. Same ingredient as Goeth, not Browder, but we call this Browder-Goeth modular version. Okay? Now we go to Kirk now. Huh? So for Kirk, we need what? We need normal what? Structure property. So from 1988, I set up the stage, which is what? The Chebyshev quantities, Chebyshev radius, center, all this with respect to what? To the module. With respect to the module. And you have to be careful. Why? Because in the case of Banach, what did they show you? This is the Chebyshev center. Huh? Yes? R of C is less than delta of C, the diameter. That stays the same. What you don't have now is this one. This, you don't have it. Why? Because this is based on the triangular inequality. So for example, to show you this, you have distance from x to y less or equal than distance of x to z plus distance from z to y. This is less than r of zc plus r of zc, which is twice divided by 2, and you take the infimum, and you will find half of the diameter less than what? Because this is for every x and y, and that's how you get this from the triangular inequality. Without triangular inequality, you don't have that, period. What's happening with the module? Don't ask me. Now, we have UC. If you remember, not all the time, in the case of Orlich, in the case of variable exponents, I showed you that UC and SC, strict convexity, are equivalent. Okay, you have UC. What does UC say? It's true that the Chebyshev center has at most one element. True. So if you have one element, you will have normal structure property. What is the problem? Is that the Chebyshev center can be what? Empty. So how do you avoid emptiness? You need compactness. In the case of Banach spaces, reflexivity, weak compactness. In the case of modular, what is the weak compactness? Weak compactness will come from what? From the dual. We don't know the dual. We're working on it right now, me and Osvaldo and Jan, in this paper that I told you about. We don't know what's the dual. They have some kind of ideas, but no, we don't have weak topology for the module, except, of course, if you go through what? Through the Luxembourg norm. But we don't for the modular sense. And therefore, you have to come up with what? with different type of compactness. And that's where Maurice Pouset and the work I did with him helped me understand this prior to what? To visiting California. So when I came to California, I thought, oh, I know how to do this without doing what? Weak compactness. So I used balls and what's known as admissible sets. Do you understand? I learned it from where? From my contacts with Maurice Pouset, as a student, of course. And we have now this theorem. Of course, it's in the same paper, but they couldn't grasp it. I'm talking about Shimon and Kozlovsky or Wojtek. They couldn't grasp it. I brought with me this knowledge, and we implemented. And so I called it yesterday for the first time, because I didn't want to bother you with this. It's too technical. So I called it raw ball compactness, but it's not. It's not called raw ball compactness. I just invented this yesterday. So don't believe if you go and say, oh, Dr. Amin, or whatever you call me, and oh, he said raw ball compactness, and you start looking, you are not going to find raw ball compactness. There is no such thing as raw ball compactness. Okay? Any question? I swear, I thought I'm not going to be able to do it within the time allocated. And I had to cut so much because I said if I do it, it's going to be the whole day, and we cannot. It's enough for you to see me for 1 hour and a half. The whole day is too much. Anyway, any question? So this afternoon during the tutorial, I really want to touch on that point because I felt bad I didn't talk about it. I'm talking about Karlovich lemma. So I will touch on it during the tutorial, and that's it. And I will be done. Okay? Thank you.
Okay, thank you very much. So now a tea break for 20 minutes. So tea is ready. So let's grab the tea, and after tea there is a talk by Professor B.C. Daju. So application of fixed point